Welcome to the 2025 Spotter Training from the National Weather Service in Kansas City. The National Weather Service is a federal agency housed underneath the National Oceanic Atmospheric Administration within the U.S. Department of Commerce. The mission of the NWS is to provide weather, water, and climate information for decision support services aimed at the protection of life and property. Even if you have not heard of our agency before, you may already be familiar with our watch, advisory, and warning products. The NWS has had an office in the Kansas City area for nearly 140 years. The Kansas City office, located in Pleasant Hill, Missouri, is responsible for 37 counties in Missouri and 7 counties in Kansas. Along with 122 other local NWS offices, we operate 24 hours a day, 7 days a week, 365 days a year, including holidays. Our staff typically consists of 17 meteorologists along with 5 support staff. During severe weather, we generally have at least 5 to 6 people working to support warning operations. In higher end events, it is possible to have closer to 10 meteorologists on the floor collaborating on severe weather products. Here, you can see 6 defined roles typically an office will use during severe weather. It really is a team effort to provide our services. Storm spotters play a critical role in the warning process for National Weather Service meteorologists. While powerful tools such as satellite and Doppler radar help tremendously, there are certain limitations that we'll review in just a few moments. Spotters are extremely important because they help to augment what the National Weather Service meteorologists see on the Doppler radar, as well as adding credibility to the National Weather Service warnings. Therefore, your accurate, timely reports are extremely important in the warning process. In most cases, the initial tornado warning or severe thunderstorm warning for a storm will be based on a meteorologist's analysis of Doppler radar and the ambient environment that the storm is in. Ideally, the initial warning and its associated call to actions would prompt an appropriate sheltering response. However, studies of human responses to storm warnings have shown that confirmation of the weather hazard is what often prompts sheltering actions. Your confirmation reports not only get relayed to the National Weather Service, but also to emergency managers and broadcast meteorologists. There are 3 main warning products issued by the National Weather Service for severe thunderstorms. The first is the Severe Thunderstorm Warning. For a storm to be categorized as severe, it must produce a wind gust of at least 58 miles per hour, or a hailstone at least 1 inch in diameter or greater. Note, only one of these criteria need to be met for a storm to be severe. Also note that lightning type, frequency, or the noise of thunder after a lightning strike does not determine if a storm is severe. A tornado warning is issued when a thunderstorm presents an imminent threat of producing a tornado. This is either based on Doppler radar indicated rotation or confirmed reports of a tornado with a thunderstorm. Finally, there is the flash flood warning. Typically, this is defined as 6 inches or greater of water flowing across roadways, but other rapid rises in water that is deemed a threat to life and property can also warrant a flash flood warning. Flash flooding is the deadliest hazard associated with thunderstorms each year. When spotting storms and their associated hazards, these are the details that the National Weather Service will find most valuable. Please note, though, that your safety must be your first priority. Do not place yourself in potential danger to observe storms. The National Weather Service will never officially deploy nor activate spotters. All reports are voluntary. At first glance, you'll notice that the important details are related to the criteria for severe warnings. If you do not see anything that meets severe criteria but is close, that can still be a valuable report to the National Weather Service. If you are observing hail and there is a large quantity that has fallen, inform on the largest size that you spot. If you can't take a direct measurement, compare the hail diameter size to a common object, such as a coin, a fruit, or a ball. Winds can often be hard to estimate if you don't have a direct observation. However, specific details on wind damage can be helpful, such as the diameter of tree limbs, the health of a tree, or whether the tree was uprooted or snapped. Specific details on structural damage is always helpful, as we can generally create an estimate of the wind speed. If you have access to social media or email, a picture really does speak 1,000 words. Spotting rotation in a storm can be valuable, even if a tornado or funnel cloud is not present. Rotation can sometimes be difficult to see from the ground, though, and in some cases, upward motion may look like rotation at times. We will show examples in a little bit of rotating wall clouds, funnel clouds, actual tornadoes, as well as scud clouds that can deceptively look like tornadoes at times. And finally, if you spot flooding, report if the water is moving or still and the approximate depth if possible. Never step into flooded waters to measure and never drive into a flooded roadway. You've probably heard it before, but it remains true. Turn around, don't drown. When it comes to reporting what you spot, the more specific details you're able to provide, including location and time, are extremely critical. When reporting location, specify if that is where you are currently standing or if that is where the hazard is located at. Relative distance from known cities and highways can be useful when reporting hazards. There are multiple methods for sharing your storm spotter reports with the National Weather Service. The preferred method is for a county spotter network to report directly to their local emergency management, who then can utilize National Weather Service Chat 2.0 via Slack. These reports then go directly to the National Weather Service office, as well as television and radio broadcast meteorologist. You may also call the National Weather Service directly with the number that is listed here. Please provide as many specific details as possible, but limit any unnecessary extraneous commentary, as the meteorologist on the phone does need to get back to the radar warning meteorologist as soon as possible with the reports. You can also send us pictures and details through social media. Before exploring storm characteristics and how to spot features, let's quickly touch on products that are available to remain situationally aware of hazardous weather in the days and hours leading up to a severe weather event. The convective outlooks issued by the Storm Prediction Center in Norman, Oklahoma provide 5 levels on anticipated coverage and threat level associated with severe storms. If you'd like, you may pause the video here to thoroughly read this graphic. Here at the Kansas City office, we generally place these into our DSS packets, which are available on our homepage, weather.gov/Kansas City. Other NWS offices also will generally share these outlooks, along with additional forecast details. An intermediate product between the SPC convective outlooks and the issuance of watches and warnings is the mesoscale discussion. While the technical details in these discussions are designed more for interpretation from meteorologists, one useful takeaway is the likelihood of a watch eventually being needed. These can be viewed on the SPC website, and for partners with access to NWS Chat, these can be viewed there when one is issued for our area of warning responsibility. Severe thunderstorm watches and tornado watches are a product issued by the SPC when conditions are favorable for the development of severe weather. The SPC hosts a collaboration phone call with local NWS offices prior to their issuance. Typically, these will be issued a few hours in advance of expected storm development. This product is county-based. The text associated with them will contain a few extra details about the environment. Let's dive into characteristics about the Doppler radar, one of the critical tools used in NWS warning decision-making. The radar sends a powerful pulse of electromagnetic radiation designed to hit weather targets such as rain and hail, and returns a signal back to the radar. There are 2 characteristics to the radar beam that limit a meteorologist's ability to directly sample a hazard. The first is that the radar beam continues to climb above ground level as it travels further away from the radar, due to properties of electromagnetic radiation and the curvature of the Earth. As a result, meteorologists are left with data that samples above where the actual hazards occur. This is where spotters come in, because you are at the surface and can verify what is happening where the radar is not directly sampling. Second, the radar beam width also increases the further away from the radar it travels. Therefore, any features that are smaller than the width of the radar beam are not fully resolved, decreasing resolution available to assess the storm features. There are several products that are returned from the radar signal, including reflectivity and velocity. The reflectivity product you are likely familiar with, whether it is from a radar application on your mobile phone or from a television news broadcast. Reflectivity is a measure of how much power the radar receives back. The more meteorological targets it encounters, the lower the power that is returned to the radar, and thus the higher reflectivity values. This depends on the size of the targets, their density, and the type of target. Typically, highest reflectivity values will come from a mixture of rain and hail. This image is a radar reflectivity for a classic textbook Supercell thunderstorm. In addition to reflectivity, velocity is another product provided from the radar signal. Picture the radar beam in pulses as a series of waves when it leaves the radar. When these hit meteorological targets, it will cause the distance between the crest and the troughs within the waves to change. This is called a phase shift, and from a phase shift, we are able to derive the velocity and direction of a moving target. Note though that from a radar, the only determination of direction we can make is relative to the radar. That is, if a target is moving toward or away from the radar. In most typical color displays, green refers to motion toward the radar, inbound, while red refers to motion away from the radar, outbound motion. For an object that is rotating, such as the updraft of a supercell thunderstorm, you will see green next to red. In this example, you can see the circulation associated with a storm near Orick, Missouri that produced a tornado. The radar is located to the southwest. There are a multitude of processes going on in the atmosphere that aid in the development of thunderstorms, but these can be broken down into three primary ingredients, with a fourth ingredient needed for general thunderstorms to become severe. Ingredient number one is moisture. In order to form clouds, you need a source of water vapor that eventually can condense into droplets to form clouds. For our area, from the eastern Great Plains to the middle Mississippi River Valley, air masses from the Gulf of Mexico generally provide our moisture source in thunderstorm environments. Ingredient number two is instability. Instability in meteorology refers to an air's tendency to rise due to differences in buoyancy. Early in the morning, the ground has cooled rapidly from the overnight hours, with a warm layer that is above it. Because cool air is more dense, the air is less susceptible to rising. We often refer to this as the cap. Through the middle of the afternoon, though, the sun aids in warming the surface at a faster rate than the mid-level air warms. As a result, the near surface layer becomes more buoyant, thus allowing air to rise. Eventually, this instability builds and breaks the cap, allowing rising motion to take the moist warm air mass, move it upward to cool, and eventually condense into a cloud. At this point, the cap has broken. Ingredient number three is a source of lift. While sunshine can help create instability, oftentimes the air needs a physical upward push to reach a point where it becomes buoyant enough to then rise on its own. Warm fronts and cold fronts are the most common source of lift for thunderstorm initiation. Moisture, instability, and lift will yield thunderstorm development. For thunderstorms to organize and become severe, we need wind shear to be present. Wind shear refers to a change in the wind speed and/or the wind direction as you move higher up through the atmosphere. Think about the winds at the surface versus the winds that occur at levels where the jet streams are typically located. These differences in wind speed and/or direction with height is ultimately what can impart spin on thunderstorms. Let's use this garden hose as a visualization. The hose is providing the upward motion, as seen by the orange arrow. Gravity, though, quickly takes over, and the precipitation falls back down to the ground. In this example, where there is no wind shear, the downward motion occurs over the same area as the rising motion. This quickly will cause a storm to dissipate, as the downward motion and rain-cooled air disrupt the source that can fuel a storm. Now, add in wind shear. We still have an updraft and downdraft, but they have become separated. Therefore, the updraft continues to provide warm, moist air into the storm while rain is occurring in the downdraft area. The lack of disruption caused by this separation allows the storm to mature. Thus, wind shear provides an opportunity for the storm to become severe. Here is an actual supercell example, where the shear has helped to separate the updraft from the downdraft. Thunderstorms exhibit quite the variety when exploring their structure, radar signatures, and associated hazards. We have general classifications for thunderstorm types, but admittedly, while observing, we may notice a hybrid of storm mode or a coexistence of all three. It is important to keep in mind that any type of thunderstorm can become severe. Single-cell thunderstorms, sometimes referred to as pulse storms, are a single updraft. These tend to produce the least amount of severe weather and do not last for an extended period of time. Recall the importance of wind shear in thunderstorm longevity. These are the storms that tend to produce localized downburst and microburst. Multicells can either form in clusters or more organized lines, often referred to as squall lines. High-end winds tend to be the most common threat, though hail and tornadoes can occur with some. Then finally is the supercell. The supercell is generally the strongest and can easily produce all hazard types of large hail, damaging winds, and strong tornadoes. A squall line, also referred to as a QLCS, which stands for quasi-linear convective system, is a type of multi-cell thunderstorm that congeals into an organized line. They are frequently associated with widespread damaging winds, though hail and tornadoes can develop with them. In this diagram, first take note of the red lines on the leading edge. The leading edge of a squall line is where the rising motion occurs. This is the intake of warm, moist air that fuels the line. On the back edge is the downdraft area. This area is substantially cooler due to the evaporation of rain and hail, if present. The contrast from the rain-cooled air mass and warm ambient air ahead of the line results in a gust front, and this is where the strongest winds tend to be concentrated. During the developing and maturing stages of a squall line, the area of rising motion on the leading edge will be separate from the downward motion. Eventually, the gust front pushes outward and cuts off the warm inflow. When this happens, the squall line is outflow dominant and usually is followed by dissipation of the thunderstorm complex. However, it can be possible to get new development from the outflow of a decaying thunderstorm complex. The most prominent feature with squall lines is the shelf cloud, and usually denotes the location of the gust front. Here is a marked picture of a shelf cloud associated with a strong squall line event. Along the leading edge, the updraft region is ingesting warm, moist air to fuel the line. On the backside is the downdraft area, where evaporation is creating a cold, dense air mass. Along this updraft-downdraft interface is the shelf cloud. The shelf cloud develops as evaporational cooling leads to water vapor condensing. In addition, you can notice the dust being kicked up by the strong winds along the gust front. Here's another shelf cloud moving into downtown Kansas City. The warm inflow air originates on the right-hand side of this photograph and moves left and upward, while the rain-cooled air is located to the left-hand side and is moving downward. Here is a video of a shelf cloud moving in with a squall line. Notice the shelf cloud does exhibit rotation, but the rotation moves about a horizontal axis in the sky. Notice that the shelf cloud gets near the camera is when the winds pick up, denoting the location of the gust front. The horizontal rotation of a shelf cloud can be an indication of a strong gust front, but does not necessarily imply an immediate tornado threat. Here is an example of straight line winds that will commonly be observed with strong squall line events. Recall, severe winds are any gust of at least 58 miles per hour. Stronger squall lines tend to produce winds between 60 and 70 miles per hour, with higher end events pushing above 80 miles per hour. The Supercell thunderstorm. This is a thunderstorm characterized by a robust, rotating updraft. The updraft rotates about a vertical axis, unlike a shelf cloud, which rotates about a horizontal axis. Supercells are generally responsible for the most significant and violent tornadoes and large hail sizes in the United States. They can also lead to extreme, damaging winds and flash flooding. In this diagram, you will notice several features that are labeled. We will be reviewing a few of the key features to spot. Notice that the storm is very large. The wall cloud and tornado compose only a small component of the supercell thunderstorm, assuming that they are present. Recall, the NWS Doppler radar in most circumstances will not detect these low, small-scale features directly. Thus, your spotter reports are extremely valuable to the National Weather Service. Here is a classic supercell radar signature via the reflectivity product. This is frequently referred to as a hook echo. The strongest supercells tends to be well-defined, but several supercells that occur in our area may not always have a well-defined hook echo signature. When viewed from a distance, a supercell thunderstorm generally takes on the shape of an anvil. Supercells often provide good visual cues that can inform on the strength of the associated updraft. Compare these two pictures. On the left-hand side, the weaker updraft does not have edges that are well defined, whereas on the right-hand side, the stronger updraft has a more notable definition at the top and on the sides. When looking from a distance, pay attention to the change in the appearance of the updraft. This will be your clue as to whether or not the supercell is strengthening or weakening. When viewed from a slightly closer distance, stronger updrafts will often take on a cauliflower-like form to it. When this is spotted, this means that the updraft is strong. A strong updraft implies that the supercell is taking in warm, moist air, which provides fuel for the storm to continue to strengthen. Remember, the rotation about a vertical axis of the updraft defines a supercell thunderstorm. This is the main role wind shear plays in developing severe weather. At times, rotation can be visible to the naked eye. In other cases, rotation may only be evident if you are recording a video and then speed up the playback of the video. But one visual cue for stronger supercells that demonstrate strong rotation is the corkscrew or barber pole-like appearance with a supercell that feeds into the updraft region, as pictured here. The rain-free base is an area that has no precipitation visible, because the upward motion of the updraft is preventing any hydrometeors from falling. In this image, it is clear to see the precipitation shield on the right-hand side, the forward flank downdraft. In supercells, identifying the rain-free base is important because most of the action is going to happen in the updraft region, typically near the updraft-downdraft interface. The updraft gives you a clear shot of what the storm is ingesting, which largely determines what the storm produces. Tornadoes occur within the updraft region. While a lot of hail occurs in the heavy precipitation shield on the right-hand side of this image, the largest hailstones often fall out closer to the updraft-downdraft interface, circled in yellow. This is because gravity forces the larger hailstones to fall earlier and do not travel as far into the main forward flank downdraft. If you are mobile while spotting, you want to position yourself to see the updraft. However, you must remain mindful of the storm motion, both direction and speed. Eventually, the precipitation shield may reach you. Never compromise your safety to storm spot. Not all supercells will have a well-defined inflow tell, sometimes referred to as a beaver tell. However, stronger supercells do tend to develop this feature. It indicates that the updraft is ingesting a large amount of warm, moist, and unstable air from the ambient environment and will likely continue to strengthen. Inflow tells are sometimes noted on the clear side of the forward flank downdraft just in front of the precipitation shield and goes into the updraft and rain-free base. Other times the inflow tell may extend further outward from there. The wall cloud is a feature that forms in the updraft of a thunderstorm. It may look similar to a shelf cloud of a QLCS, but is not nearly as long. The wall cloud forms in a very similar way though. It is the result of evaporational cooling causing water vapor to condense. Oftentimes, the wall cloud will point toward the area of the downdraft or the precipitation shield. This often makes it easier to identify the updraft-downdraft interface. If a supercell produces a tornado, you will often see it develop under the wall cloud. The wall cloud itself can often demonstrate visible rotation. Again, looking into the updraft region, you can tell a lot about a storm. It is possible for a strong rotating wall cloud to form, but no tornado to occur. Funnel clouds can often be spotted underneath a wall cloud in the updraft region. And finally, do you recognize this feature here? If you guessed inflow tell, you are correct. Notice how this feeds into the updraft region, where the wall cloud is also attached. In this time lapse of a supercell thunderstorm, the rotation of the updraft is apparent. A wall cloud develops and points towards the forward flank downdraft precipitation shield on the right-hand side of the imagery. You can even notice an inflow tell into the updraft region. From the left-hand side, you will also notice a clear slot. This is the rear flank downdraft. At times, this can be difficult to spot. Sometimes it will be visible if it is kicking up dust. The rear flank downdraft can often become a hazard if mobile spotting. Oftentimes you'll be in clear conditions, but suddenly you will find yourself in 70 mph or higher crosswinds. If you're able to spot a strong rear flank downdraft that helps to intensify the inflow into a supercell, the probability for tornadogenesis may be increasing with the supercell. Let's discuss the rear flank downdraft further. This feature plays a key role in generating rotation within a supercell thunderstorm. Thus, the rear flank downdraft plays a large role in developing the hook echo signature on radar reflectivity. If you are mobile spotting, it is imperative to maintain situational awareness of storm motion, both speed and direction. In this particular case, if you are south of the main updraft, with the storm moving due east, you would remain outside of the path of a potential tornado. However, with the rear flank downdraft, you run a greater risk of encountering very strong crosswinds, sometimes in excess of 70 mph. Another note regarding supercells is that they can easily undergo a change in motion. You never want to assume that a supercell's motion will remain steady. Like in the time lapse, you can see the rear flank downdraft via the clear slot that is wrapping around the storm. In this picture, you will notice a wall cloud in the updraft region, with forward flank downdraft toward the right-hand side where hail and heavy rain is occurring. While a tornado has not developed yet, you will notice a lowering underneath the wall cloud. This supercell is showing increasing tornado potential, with the strong rear flank downdraft helping to increase the rotation, as well as the inflow tell indicating that the storm is still ingesting warm, unstable air. Tornado. A violently rotating column of air that extends from the base of a thunderstorm and comes into direct contact with the ground. This picture illustrates very well how small of a feature a tornado is relative to the rest of the parent supercell thunderstorm. Notice the tornado has formed in the updraft region of the thunderstorm, and why it is the critical feature to view while spotting storms. In order to be considered a tornado, the rotating column of air must be both in contact with the ground and attached to the base of a thunderstorm or rain shower. If the rotation is attached to the base of a thunderstorm or shower, but is not clearly in contact with the ground, this would be a funnel cloud. You do not necessarily need to see a fully condensed cloud to have a tornado. If you see a funnel cloud, that is, rotation attached to the base of a thunderstorm or shower, clear air in the middle, and then dust or debris present at the surface directly underneath it, that is a tornado, as the rotating column of air is in contact with both the ground and the base of the thunderstorm. Oftentimes in our region, there will be a lot more rain around supercell thunderstorms, leaving the updraft not as exposed as in a few of the previous pictures. However, the same concepts still apply. Here, we are looking into the updraft region, and we subtly see rising motion just to the right of center in this video. Note that this video is sped up, which makes the rotation more visible. Eventually, within the updraft region, a tornado develops. The area of rotation is in contact with both the base of the thunderstorm and the ground. One of the most common features that incorrectly gets identified as a funnel cloud or a tornado is a scud cloud. Scud clouds may often take on a tube-like shape that looks similar to a tornado or funnel cloud. Scud clouds, though, will not show any rotation, though they may move upward when adjusted by an updraft and give the appearance of rotation. Scud clouds can be found anywhere nearby a thunderstorm, and is possible for them to touch the ground. Scud clouds are not associated with damage. In some cases, scud clouds can turn into a wall cloud that attaches to the base of a thunderstorm within the updraft region. In this still picture example, the scud cloud is hanging down from the base of the thunderstorm. The general shape may look similar to a tornado or funnel cloud, but notice the edges of it are not smooth. Actual tornado and funnel clouds tend to be smooth and laminar when they are rotating. In this animation of scud clouds, you will notice the rising motion may look like some rotation. Again, though, notice that the edges are not smooth and laminar. While some become attached to the base of the thunderstorm, they do not persistently rotate about a vertical axis and never come into contact with both the ground and the base of the thunderstorm. One useful identification of scud clouds can be to estimate the updraft strength. An updraft steadily ingesting scud clouds can be a sign of a strengthening updraft. That will conclude the presentation content for the 2025 Spotter Talk. Up next, the video will play through a series of quiz questions. You'll have approximately 10 seconds to come up with your response. That will conclude the spotter training and quiz. If you would like to print a spotter training completion certificate, you may visit this link on the screen. On the page, you will see two text fields, one for your name and one for a password code. The code is listed right here on the screen. The certificate does not grant you permission to violate traffic laws, enter restricted areas, or trespass private property. The certificate does not provide you any affiliation with the National Weather Service or NOAA. Thank you for completing the 2025 spotter training from the Kansas City National Weather Service. Remember, never place yourself in danger to spot storms and report features. If you are in a dangerous weather situation, please get yourself to safety first before sending in your report. No report is worth compromising your safety. A delayed report can still be valuable to the National Weather Service. We look forward to hearing from you this thunderstorm season.